Physics and Technology, and many of you may not have heard of it before, not as famous at MIT, but other graduates included at least 7 physics Nobel Prize winners, including the famous Kapitsa, Landau, Sakharov, and Ginsburg. Eugene completed his PhD in 1985 at the Space Research Institute, also called ICI, and presumably Rashid was his thesis advisor. In addition to a continued position at ICI, Eugene is still on the staff of the Max Planck Institute for Astrophysics, MPA. In addition to a series of prizes and awards, Eugene was elected a corresponding member of the Russian Academy in 2008, full member in 2019. He has a wonderful sense of humor, and I hope you'll figure that out during his talk. He brings us really very, very cute ideas to his astrophysics. He finds entertaining ways to really illustrate the physics. And you can see this even in his title. He begins the North Polar Spur and steam locomotives. And so I give you in a few more minutes, and I can't keep ad-libbing like the people do on the news, Eugene.
Thank you for the kind introduction. What you cannot see in this screen.
Yes.
We're almost there, sorry. Okay,
Yes.
Okay.
so on Zoom, if you can go on Zoom, so there is meeting ID and passcode.
Yep. All right.
Yeah,
so the
it's
The
on.
meeting
899.
is not typing. Yeah, on the others.
There we go. Gosh. Is it typing?
Just leave that up.
899
4917
4917
6599
6599.
passcode
Sean. Passcode.
69 1600.
Right, I'll take a picture. 69. Okay, yeah. 69 600. Okay. All right.
That's fine. The worst case scenario is. Yes. Where does the ball then? Yeah.
So they're plugging it downstairs directly.
Yeah, yeah.
It's just on
Plug it in.
Recording.
Oh.
whether this is really unique on the sky and whether their symmetry matters. You see that it's here, but there is something here, but not that much. Here there is not that much, right? And here there is not that much. Does it matter or not? And to do so, let's take our galaxy as it is. And now let's do cosmetic operation to our Milky Way. We are going to cut the piece from here and flip it to the north. The galaxy agrees. Well, so and then what we do, just we replace just this piece. So now the galaxy is nicer, much nicer. It's absolutely symmetric. There are no left and right asymmetry. Just small touch. This means that North Polar Spur is really unique. You just change a little bit, but it's unique. And now you can see actually when it's gone, you see the other structures are becoming more prominent, right? This is velar region, this is thickness region. So they look like kind of scaled down version of the plumes. And so that after this thing, we restore the galaxy in the original form, and you can say indeed, North Polar Spur is the most prominent. Right? Once we remove it, the galaxy is becoming much more symmetric. The symmetry is there, but comparing those regions with that region, we can say that there is possibility that it's actually, this is not kind of absolutely outstanding, but the biggest one among so comparable things. Maybe that's the most prominent region among similar ones, but we know for sure that those are not related to galactic century. Velar and Cygnus are not there. Well, there is, of course, there are subtleties related to the thermal emission in radio band and non-thermal emission in radio band, but we'll put it under the rug. Okay, so on top of this, there are X-ray maps, and this is the X-ray map, right? And that's the region where North Polar Spur is, and you see the kind of nice correlation. Okay, so there is a lot of X-ray emission, and what you can do now, and again, there is asymmetry. So this is bright. Here you don't see comparable brightness. Okay, now what you can do, you can take the piece of the sky, and this is again radio image, right? That's North Polar Spur. You just draw circles, put the center somewhere here, so the curvature of the North Polar Spur is nicely described by those circles, and you make radial profile of radio emission and also emission in the line, well, the energy band from 0.5 to 0.6 keV, which contains helium-like oxygen 7, right? The most prominent line in the diffuse emission of the galaxy. And you do the same in the other bands. For example, this band. This band includes the ion lines, right, of L shell, right? Neon-like iron, which, like helium-like ions, is also present in the wide range of temperature. You can do this, and you can just make the radial profile, which is shown here. Again, this is distance from the whatever center we choose, right? And those are the radial profiles in different energy band. This light blue is oxygen 7, helium-like oxygen. And this is far away from the North Polar Spur, and that's where the North Polar Spur starts, right there. And then it goes up and down into the entire region covered here. And if you take the other bands, like they take this band, which contains some of the iron L shell lines, this is this one. It actually goes up at the same time as the oxygen 7, but then it just slowly grows. Well, if you like non-equilibrium ionization, you can interpret this in these terms. But unfortunately, the structure is much more complicated. So instead of, for example, oxygen 7 doesn't make a shell, right? It goes up, but then it flattens. Right? And so there is not so simple. So you can interpret this as the effects of non-equilibrium ionization, but you can also interpret this that there is just multi-layer structure. So there are kind of different temperatures present in the system. What you can do also with this, you can first subtract the background level. related to the galaxy from this region, and then renormalize all profiles at some arbitrary points. And that's shown here. So now you subtract this level, right? It's 0 here. Now you normalize an arbitrarily chosen point, and you see what is happening. So they all start at the same time, but then the softer bands, so oxygen 7, oxygen N, they are just reaching peak earlier and then flatten. And those which are associated with the ionization ions, they grow it again. So if you want, those are signs of non-equilibrium ionization. Right? The only trouble is that non-equilibriumization is more important for the objects which are close to you than far away to you, because the X-ray emissivity scales well with so you observed given surface brightness, and it's proportional to the square of the density times the size, right? So that the electron density is going to be inversely proportional to the square of the distance, square of the linear size. But the ionization parameter, which is product of the time by density, it includes time, and time is inversely proportional to the, time is, size divided by the velocity, and velocity you know from this temperature. And therefore, the objects which are close to you can be non-equilibrium. The objects which are 100 times further away should have ionization parameter much larger by, factor of 10 at least. So this is potential way of differentiating things. I will not go into details. I still believe that this is kind of far away. It's not 100 percent. Well, but that's okay. And you can just kind of, there are a couple of, several measurements will arguing that this is the non-equilibrium ionization, but if you have layer structure, so you might actually mimic this with other means. Okay, that's it. Now, the question, what this North Polar Spur looks like, are there any on Earth analogs which look exactly like North Polar Spur? And that's one example. This is great far of London, right, by an unknown artist. And this is what happened when just people didn't close well enough that they opened the bread, right, overnight, and the whole London was burning. And this is North Polar Spur, and you see that it's actually, of course, I choose the colors, right, but they look exactly the same. Even if you see the plume from North Polar Spur continues somewhere. But this means that in principle, so if you look at the structure, you can interpret it differently. You can interpret it as not the shock, but some flow of the hot gas. And that's kind of the whole idea behind this. And as I said, there are no agreement about distance, no agreement about details, but most of the people agree that this North Polar Spur is a shock. And when people agree, all people agree that this is a shock, it's time to kind of try to say maybe this is not a shock. At least you will have a lot of kind of arguments with people. And so again, Churazov, who formulated this problem in the following way, that owing to the shock age shell-like morphology, then this is interpreted as a spherical shock wave driven by explosive energy with at the loop center. And this is absolutely valid and possible interpretation. So we have just 50% chance or whatever that this is really true. But let's try to kind of oppose this notion and ask the question, do we know examples of sharp-aged morphology, which is not a shock? And we know, we have people doing clusters here, right? And they're called fronts in galaxy clusters, right? They're very sharp, and they're not shocks. And they're not shocks, and why they're called fronts? Because the brighter side is colder than the fainter side. So for the shock, you expect the compression, maybe adiabatic compression at least, or maybe higher, just dissipation, the shock, that the denser part is going to be hotter, right? That distance. For the cold fronts, this is opposite. So this side is colder, pressure is continuous, so it's contact discontinuity, and this side is brighter just because the air squared is larger. Okay, so of course there are always, and there's always the question why there are no huge Kelvin bonds instability there, and doing this as well in just normal life. Well, you see this thing, right? And this is remarkable how smooth the water flow here. And the key here is not the surface tension actually, but the acceleration of the fluid along the surface there. And well, you can we did this long time ago with Neil and Nagamov, and then simulators as well. So what you have consider potential flow, right? So you have a flow of hotter gas flowing around the colder gas. And you have stagnation point right here where the velocities are zero. And velocities are zero, but then as you move along the interface, the velocity is increased. So that what happens, and if it's subsonic flow, the increase of the velocity means that you stretching fluid elements. And if it's subsonic, when you're stretching the element along the flow, it has to be compressed perpendicular because the density doesn't change much in the subsonic effectively in compressive flows. Moreover, because if you just flow over a sphere, it means that you also stretch in lateral direction because the same fluid element now have to cover the larger perimeter, right? So in 2 dimensions, you stretch along and across, and then you have to suppress in particular direction. And also the wavelengths of all perturbations is increasing with distance, right? You see small perturbation, but that's becoming larger and larger. And this is similar to what happens in the gravitational stability in the universe, right? The universe expands, and the instability, like the halos are formed. This is not exponential, but this is parallel thing, just because you continuously stretching things. And the same is happening here. Instead of the normal Kelvin bonds, exponential instability, you have linear growth, much smaller, and in addition, the kind of suppression in this direction helps you to actually suppress the instabilities. When you add a bit of, certification, gravity, or a bit of magnetic field, or a bit of viscosity, you can actually make just nice, smooth interface. And you can see this simulation by Sebastian. Well, you have Kelvin bonds eddies somewhere there where the acceleration already not effective, but this part remains sharp. And we see this in other simulations as well. So it's not a problem, but so this means that, we can create in principle sharp interfaces, provided we have special conditions there, and those sharp interfaces are not going to be shocks, but they can be contact discontinuity. Okay, so it's possible that this is not a shock, but a contact discontinuity is then no pressure jump. And now we have a problem, really a problem, because for the cold fronts, the brighter side, North Polar Spur, has to be colder than the gas outside because it's brighter. And you compare the spectrum outside North Polar Spur. This is the classical spectrum. This is diffuse emission from our galaxy. This is oxygen 7 line. Right? Oxygen 8 is really just small, and the typical equilibrium temperature is 0.15 keV or something like that. You go deep into the amperes and you look at the spectrum, and you see that now the oxygen 8 has comparable intensity as oxygen 7. Now there are lines of L shell of iron, and you have to have the temperature of half a keV there. So this spot is brighter, but it's hotter. So does it mean that this is shock? In principle, yes, if the abundance is uniform. But if you want to save this model, this contact discontinuity, what you have to do, you have to increase the abundance in the North Polar Spur gas, hot gas, by a factor of 10. Right? So this is kind of illustrated in this picture, if you just increase the abundance of the gas here by roughly order of magnitude, compare the diffuse emission in the halo of Milky Way, you can reproduce the relation between intensities without changing pressure, because metals, they don't contribute to pressure, they contribute to emissivity. And at those temperatures, actually Bremsstrahlung, you don't see it Bremsstrahlung. You see the emission of lines, you see two-photon emission, the recombination continuum, but not the proper Bremsstrahlung. So you don't know the abundance of elements at those temperatures. You are dominated, heavily dominated by lines and things like that. Okay, so we don't know the right answer, but if we believe in this model, we need something hot and with a lot of metals. Right? And do we have on the Earth things which produce something hot with a lot of metals? Yeah, we know. So it's actually what is polluting air. And well, we see that this stuff is rising just because it's hot and buoyant, and it's dark because it contains a lot of carbon or other bad things. And so this is on the Earth, and the question is whether we see any evidence for something like this in the direction of the North Polar Spur, or more correctly in the galactic plane, in the direction toward the base of the North Polar Spur. So that's the center of the galaxy. That's we are here now. The 30 degrees is roughly where the North Polar Spur is attached to the galactic plane. And this is the line of sight, right? And you see it's actually crossing the various arms where the bar in the galaxy, right, is interacting with the spiral arms. And so those are the regions where the star formation is believed to be really intense. And you can go to the masers with the precise distances, and you see that again, this direction roughly. This direction is tangential to the one of the most actively star-forming region. And the most famous star-forming region there is W43. And this is one of the most intense star-forming regions of the galaxy. And so the idea is that it might work as a steam engine, which produce a lot of hot and heavily enriched by fatty elements, gas, much higher abundance than the gas high up in the halo of the Milky Way. And this is the gas which actually just like fire in London, while this gas is moving up and then forming a North Polar Spur. And then we are just close to the kind of well-developed picture of the superbubbles, the chimneys, fountains, and things like that, where the localized region of intense star formation are producing overpressurized regions. Then they break on one side and then expel the gas, and which has some momentum and also has buoyancy because the entropies are much higher. And of course, it's enriched. Now we can just go further and ask the question, can we simulate just the motion of the hot bubble, which you put into the halo of the Milky Way? And we can use, again, go back to the cluster analogy and do what we did with Bill Christine and Hans Boehringer when we were looking on the first papers on Eugene feedback, and then with Marcus, Rügen, and others. We said that, well, if you have in the hydrostatic atmosphere massless bubble, basically hot, let's assume it's massless, so that because it's massless, eventually in the steady state, the sum of all forces acting on the zero mass has to be zero, right? Otherwise, it will be accelerated to the infinite velocities. And that's shown here, right? So on one side, if you create a bubble, the pressure gradients acting on the bubble, and if the bubble moves with respect to the fluid, they're going to be high dynamic drag. And that's high dynamic drag, and has to be compensated by the pressure gradients. Okay, so and the whole idea is that all this shock gas, all the non-thermal particles are mostly produced during formation of the kind of these bubbles, and then they start moving and then start interacting with the environment. Okay, and this is basically again illustrated here. So what happens to the bubble depends on what happened, whether there is a wind or not, right? In this case, there is steady atmosphere. So you release the bubble, it goes up. Here, the train moves, right? The air is still, but train moves. And so the gas goes, then it joins the kind of the air, which it doesn't move, right? That's why here. And in this case, the train moves and there is a wind, which kind of in train bubble and move them. So we can just do this and now I'm coming to the kind of final picture almost. So that we have trains, star-forming regions, which are moving either with stars or with the pattern speed, if they're moving together with the polar. They release gas, which is hot, metal-rich, and buoyant. And now we ask the question, where it will move. If there are no motion of the gas in the halo of the galaxy, it will just kind of do this. It will go up and then stay with the gas once it decelerates. But in reality, so if the gas is rotating in the galaxy, we can try to use this as I infer the rotation velocity of the hot gas, even without measuring velocities. You like to measure velocity of the gas, but if you cannot, we can use this suture. And so in the rotating coordinates, right, we just introduce centrifugal force. This is a cylindrical rotation, simple one. This is the pressure gradient, and this is gradient potential, and this is the centrifugal force. And this what acts on everything in the atmosphere. In a static atmosphere, well, those terms are just. Now suppose you put the massless bubble into the same direction. So this works, right? This works, but the gradation potential, okay? Massless bubble doesn't know about the gradation potential. The rest of the forces are there. The question is in which direction the massless bubble will move in a rotating system, because there are no centrifugal force acting on it, because there is no mass. Here, well, the atmosphere in hydrostatic equilibrium. Now you put massless bubble. Which way it will move? Because there is no centrifugal force, right? But the pressure gradients are there. It's going to move to the center. And this is used in the water cleaning systems to separate stuff which is more floating from stuff which is less floating. But well, it's kind of, it's not obvious. So what you can do, you can go take just a glass of water. That's my hand. And so that's the simulation of the rotating fluid stratified. And you see what bubbles are doing. All the bubbles are just moving towards the center and, well, slow motion. But you see that this is the stream of bubbles. They all collected to the center without any further kind of interaction. That's because they don't know about centrifugal force. They're only affected by the pressure gradient. Okay, so if so, that you can just take the non-rotating halo gas, and then everything will be just well, either density surfaces will be equipotential surfaces, or rotating gas in the galaxy. Then it will just more complicated shape because of the presence of fluids. Then you put bubbles there, and you see that, well, zero velocity rotation. Then, well, the gas, the bubble will move just down the pressure gradient. So along just perpendicular to the potential, equipotential surfaces. If there is rotation, so it will start moving toward the center. And if it's really if the gas rotates with the same velocity as stars in the galaxy, it will make a spiral and eventually end up in the center. Well, this is of course toy model, but that's how it works, right? So depending on how quickly the gas is rotating in the halo, we can actually infer the velocity of the rotation. Okay, there is of course the additional thing that, well, that was we were talking about a single bubble, but in reality, this is composition of many bubbles. And you can just individual bubbles convert into trajectory of the stream of bubbles. This is one thing. And another thing that you have to take into account that actually we are moving with the sun on one orbit, and all those star-forming regions are moving on the other orbit. Then you have to recalculate everything into a frame, which is trivial, right? And with that, you can just make this calculation, ignore all the criticism that this is not realistic, and make the trajectories, expected trajectories of bubbles on the sky plane. Right? So if you put the bubble, if you release the stream of bubbles in the Cygnus region, it's very close to us. And what you'll see, just stuff is moving almost up to the zenith, because we are just really next to this region, and we're moving almost with the same velocity. Goes up, and goes up means to the galactic pole. If we release in the Vela region, it will be more complicated trajectory. It's just because the system is not symmetric. The rotation of the galaxy imposes certain kind of asymmetry in this, in our view on the trajectories. And so that, well, here is Vela, here are, well, the structures we just saw, mini North Polar Spurs, and well, they're just not right. And those various trajectories are just correspond to various distances along the line of sight. Well, and various distances in the projected coordinates, and also different distances along the line of sight. And you see that they're actually forming, kind of in this simple toy model, they're forming North Polar Spur quite naturally, right? They're just, well, there is a complicated question how long they survive, or how well they mix with the ambient gas. But at least if you just put really a couple of steam engines into the galaxy, they eventually will produce the structure which look like North Polar Spur. Okay, and so that another way of looking at this, you can look at the synchrotron, polarized synchrotron emission, which is cleaner in principle picture. And they have those structures which are kind of crossing the galactic plane and then making just nice structures. And this is again a couple of some steam engines we put along same direction, about 30 degrees away from the galactic center. And you see that, well, some of them are just really have gentle shapes, which really looks like the structures we see in polarized sky. This is, of course, all toy models, but this is interesting that you can create this structure like this. Okay, so that's the kind of I'm running to my conclusions. So there are still kind of various possibilities. One is that really galactic center of Sagittarius A star is powering everything what we see. Right? There is also a possibility that instead of Sagittarius star, there is star formation episode 5 or 10 million years in the galactic center with similar energetics. And so that what we see is the forward shock. Right? This means that it's by definition transient. So the termination shock can stay, right? Contact discontinuities move slowly, but the forward shock moves away as quickly, right? So you can't stop forward shock. And so that all those variants we see a kind of we might interpret what we see in radial image rays as the forward shock. And that's what we see also in galaxy clusters in simulations, and so also in observations. This is absolutely valid and possible. And it predicts that this is transient phenomenon. We can try to do something more kind of less transient, right? For example, M82, right? It's, of course, it will not last forever, but there is no structures. Well, forward shock is somewhere outside this picture. The rest is kind of quasi-static, like more or less like this. So that's what I'm advocating. So there is star-forming regions which are arranged in the form of rings or something, which are then creating the hot flows which goes up and down on the galaxy. And this is again similar to the this structure, and this might be quasi-stationary. It might varies, of course, depending on the particular arrangements of the star-forming regions, but there is no principle it can last forever. And there is still possibility that this is supernova. It's not closed. Well, I don't believe this, but still might be there. And of course, because of the kind of, we are talking about the large scales, it's possible that there are overlaps of several features which are actually unrelated, and we are trying to say that they are connected, but they are not. Okay, I'll probably stop here and happy to chat when discuss it.
I hope people found that entertaining. We'll start in the back, work frontwards, we're gonna go back to main turn.
Yeah, thanks, Eugene. Yeah, so yeah, my next occurs is initial angular momentum. So I was wondering, so if the bubble is multi-phase, so if the bubble is multi-phase, would you expect that the different phase can carry different angular momentum, could you follow different trajectory?
Well, in principle, yes, but this is, it's why gravity stops short of this. So I think that there are so many assumptions and so many simplifications already there that I think that most of what I said is wrong. But the fault is it's not fundamentally wrong, but there is something more complicated, like you're saying. Well, it's possible that with some additional things might become more realistic. But I didn't really check those possibilities.
Eugene, I got one question for you. I'm not sure I fully understand the analogy between this bubble and the smokestack and the smoke coming off the stack. And in particular, given the fact that the filament is a bit hotter and the path length, any path length you assume through that filament is going to be a lot smaller than whatever the ambient gas is. Why isn't that filament enormously overpressurized relative to the ambient atmosphere? And what's confining it to allow it to rise like that? Okay, I mean, just the fact that it's brighter and hotter, and essentially smaller. It seems like it should be enormously overpressurized. I mean, doesn't that mean that it really actually strengthens the notion that it's a shock and not a?
Of course, but as I said, this might kill this model if the abundance of the gas in the halo and inside this region is the same. Then your actual
Okay.
So you can't avoid it.
Okay.
And the idea is that the abundance in those plumes is factor of at least 10 larger than in the halo of the Milky Way. So in the Milky Way, so it's 0.1 or less.
So the densities may work out, but if the abundance
Absolutely.
is
So
scaled by a
depends on
large
the
factor.
And then, as I said, we never see Bremsstrahlung at low temperatures. We always see, well, unless the abundance is less than 5% of solar, we never see proper hydrogen electron Bremsstrahlung.
Yeah. Let's be very clear though, with silicon-based instruments. If we had something that had better resolution,
Yeah, so if you, well,
for example.
For example.
so the answer, the easy answer is to measure velocities,
Yes.
of course, because if you see, if it's really forward shown, right? When you see through, you should see two components separated, right? And that's in the proposal, which, and eventually people will do this, that's for sure. The trouble is that kind of this is bright, but the surface brightness is not that large.
Yeah, no.
It's huge. So if you, well, Dan McCammon is his, well, collimator, right? That's the thing.
Yeah, it seems bright, but if you put like Chandra XMM field of view in that.
Yeah.
In a small region.
Absolutely. So it's really 1 radian or just quarter of radian field of view, just collimator, high spectral resolution.
Because that's hundreds of thousands of square degrees, right? 100.
Yeah, it's up to it's over there, actually, it's go to, well, 85 degrees. And if this is galactic plane, it's right there.
Yeah.
It's just amazing when we think about the galactic center, we think it's over there, no, it's here. So it's
So on a related question, sorry, I don't need to be taken up, but it's time, this is just really great. Is it, since this thing must extend well out of the plane, I mean, could we actually see these in other galaxies, say edge on galaxies or face on galaxies?
So M82 would be just, it's overshoot the
Yeah,
thing, because we see beautiful outflow, right? But this is a tiny galaxy with a large star range, right? So, and there are galaxies which should look like this, but not that kind of, not the every galaxy. M31, it has lower star formation that we have. It has something, but not comparable to this. But so still, velocities is a sure thing. That would be just the full answer. The non-equilibrium ionization, that would be just really in idealized case, with spherical symmetry. That would be also full answer, because it allows you to determine the product of the time and density. But the trouble is that it doesn't look as perfect shell. So you just,
Yeah.
you can try, but this is still kind of not absolutely clean experiment.
So are there any online questions,
Jim, I don't see it.
Yeah, that was really fascinating. Can you expand a little bit on the north-south symmetry? So why don't we see that? That's
Because if there is star formation and super bubbles in the galactic plane, you never know which side which you open first, right? Because so this thing is going to expand and then break through, and need not to break through simultaneously thousands of miles. And we do expect it's more likely that it will expand in one side, and therefore, in general, you expect the kind of somewhere here goes up and another place goes down. But if there are super pooper or something, which might break simultaneously to the north and south, I think that that's still possible.
There's been some recent work showing that our local bubble might be a local chimney with an outbreak to the north. Anything we can learn from this to understand that, or vice versa, our local bubble to see what matches with this this object as well?
Yeah, well, in principle, yes, but the still, so that if the association is the place where the bar is interacting with square points is correct, still there are, well, this super bubbles are just really a factor of, well, really more powerful than what we have the. But in principle, yes, so that
Just scale.
apart from the scale, yeah.
In this model, would you expect a temperature gradient along that?
The gradient of what?
Temperature.
Well, in principle, yes. In principle, yes. It so if you go high up, right, so that the overall pressure might go down. And yes, and the question whether we see it or not, well, this is open question.
Because you talked about the oxygen 7 and 8 lines,
Yeah.
so that would be a diagnostic, but I don't know if the.
Yeah, well, so, yeah, so what I can say that when we just closer to the plate, it's in the temperatures are inside are higher than up there, but not to the level so that I can just answer definitely the question. Okay, that's absolutely valid question. The other valid question is, so if you just consider a single bubble, it most likely will break up and mix. And this thing, either a sequence of bubbles, it might be form at the end an envelope of the heated gas. This is one thing. The cooling time is long. That's not a problem. But the overall dynamics, so how this gas socializes with the divinity they have on velocities. Then we close measure velocities. Then we close the discussion, and I'm happy.
Everything will know one way or the other, yeah.
John can weigh that.
So I wonder, you could potentially certainly be to there the absorption lines.
Absolutely. Absolutely. Yeah.
So this is a phenomenon with a characteristic timescale of sort of tens of millions of years. Okay,
That one,
so you had alluded to the asymmetry in the northern and southern parts of the galaxy. So you're saying if we took a movie of this over 100 million years, we would see these things go off at random, basically. And so it's a pure statistical accident that it's northern hemisphere asymmetric.
absolutely.
And if we took a snapshot tens of millions of years later, it might be opposite or not.
Absolutely, I'm happy to wait and see. Yes, that's right.
Yeah.
So on average, but still, so if there is a bar, and if the bar determines the stuff on the regions, right? And the bar is moving, is a pattern speed, gain, so that we are talking about similar time scales and rotation of the sun galaxy, and slightly shorter. Longer, so there has to be always some stuff on in image there. Maybe just this time, you will see the picture slightly change. Maybe it's actually kind of just rotates like this, and you always see different angles and sometimes translation, but yeah.
Ralph, again,
One more question, Eugene. Where does all this enriched gas then end up? You said it's sort of, if you use the analogy of the spinning water, it's sort of, along the axis center, but I mean, would this be a mechanism for dumping essentially all of this enriched gas in the center of the galaxy, then that would form stars again? Is that,
Well-
look at all this longer term, or would it blow it out in some way into the halo?
Okay, no. But so the idea about just moving stuff to the center was to see whether we can form the inner part of the residual bubbles, so fluid bubbles, and some place between the Fermi, even included Fermi bubbles, because if all this kind of low density stuff goes to the center, you might kind of preferentially form something, maybe then to try to make a channel. Maybe it will socialize and the density will become larger and then it will cool. That's I don't know. It's just too.
Another problem, really.
Yeah, it's speculation, even for me, yes.
It's another problem.
we thank you again for something that's really novel. Thank you.
Yeah.